Hello, my name is Eric Miller. Today we're going to be covering some organic chemistry topics. Those are functional groups, aromaticity, IR, and NMR. To start off, the different functional groups that we're going to be taking a look at today are alkyl halides, alcohols, ethers, thiols, sulfides, amines, aldehydes, ketones, carboxylic acids, esters, and arenes, or aromatic rings. Now, the reason why we're going to take a look at these and the reason why they are so important is because these functional groups, different compounds and different species that can be categorized into each of these functional groups, typically behave the same in different types of reactions, which will be covered in a different presentation. So the first functional group that we like to take a look at is the alkyl halide. You can see here in the alkyl halide, let me get my pointer tool. You can see here in the alkyl halide that the X right here is pretty much any representation of any halogen that you can see down here at the bottom. Then the R, which is on the left-hand side there, is any representation of any carbon chain. The 1, 2, 3, 4, infinity carbons. Now, I think I have an example here. In terms of naming, these are pretty simple to name. I believe in the presentation before this one, we covered alkanes, alkenes, and alkynes. And one of the things that we went over with that one is how to name this 2-carbon species here, and we said that was an ethane. So normally it would be called ethane, but since we have this other species up here, the halide, we name it a little bit differently. You see down here at the bottom, ethyl chloride is one way to name it, and then chloroethane. You can see this. You can see that ethane here the best, and then also this ethyl, which means the 2-carbon species. So that's 2 different ways to name that one. You can either name it by just taking ethane and putting chloro in front of it, or you can take the ethyl group and then putting the chloride after that. The same would be true if it were to be fluorine, maybe ethyl fluoride or fluoroethane, and then bromine, iodine, etc., etc. Moving forward to the next functional group will be an alcohol. Now, the alcohol is typically one of the easier ones to see because of this OH group on the right-hand side. Once again, the R group is just a carbon chain. Doesn't matter how long that carbon chain is. A similar way to name these as the alkyl halides is to take a look at the longest carbon chain. In this case, once again, it's a 2-carbon chain, so if we were to name it as an alkane, it would be ethane. However, with the OH group on the end there, it takes the ending of alcohol, which is OL. You can see up there at the top left. So if you were to name this, you would simply take the ethane, take off the E, and add an OL. So it would be ethanol. Secondarily, another name, which we kind of saw a little bit earlier as well. So we've got the ethanol. You can also call it ethyl alcohol. So that's just taking a look at the 2-carbon species again, and instead of naming it the ethane, it names it ethyl and then puts the alcohol on the end there. Moving forward again, so the ethers are, the way I learned it was there's a carbon chain on either side of the central oxygen. Now, I don't really like the way they have this little diagram there with the prime, because that kind of shows that there should be 2 different carbon chains on both sides of the oxygen. However, you don't really have to have 2 different lengths. So this can be 2, this can be 2, and I believe that's the example I have over here. Yes. So you can see you have 2 ethyl groups coming off of each side, one on the left and one on the right. And how would you name that? Actually, this one can go by a couple of different names. Diethyl ether, that's just the IUPAC name, where it takes each R and it simply breaks it down. And so, say if it was methyl on each side, it would be dimethyl ether. etc., etc. But in this case, it would be diethyl ether because each side are 2 carbons long. And actually, this diethyl ether is the most common ether, so it's most commonly called just ether. Okay. Moving on to the thiol. This is the first of the next few are actually sulfur containing. So this is the most simplistic one where we have the hydrogen up at the top right, and the sulfur, and then the carbon chain on the left there. Okay, and so this is an example. So ethane thiol is how you would name this one. So pretty much since the hydrogen is on the hydrogen is attached to the sulfur, you pretty much just see how long the carbon chain is attached to the other side. So you can see this one has 1, 2 carbons. So that would just be ethane, and then you just put thiol at the end of it since it's has the sulfur. Now it shows. Now it shows. Let's see, 1, 2, 3 different carbon chains. However, this doesn't really have to be 3 different carbon chains. It can be 3 of the same carbon chains coming off the same. It can also be hydrogens, which actually the example I have here has a hydrogen coming off as one of these R groups. And then the other 2 are 2 ethyl groups again. And so in order to name this one, this would be diethylamine. Now if this hydrogen right here were to be another ethyl group, this would simply be triethylamine. So you can see how there's basically they just name the substituent that's coming off of the nitrogen. Okay, moving forward now, the next few functional groups that we take a look at all have this carbon double bond O, which is a carbonyl bond there, and so each one of these has the carbonyl. The first one we're going to take a look at is aldehyde. Now the aldehyde has the carbonyl in the center, and then it has a hydrogen on one side and then a carbon chain on the other side. Now the easiest way to name these, you're going to take a look up at the aldehyde. You're simply going to take the carbon chain that is coming off of the hydrogen on the right side, and you're going to take that and change it to, say, for example, this one is 1, 2, 3, 4 carbons long. See the carbons there, 1, 2, 3, 4. So that one's 4 carbons long. So normally if it were an alkane, we would name that butane. However, since it is an aldehyde, we would name that butanal. The same thing would be true for propanal, pentanal, etc., etc. The reason why these are always, you're just going to take the carbon chain, as to see how long that is because of this hydrogen here. The very next carbon directly next to this hydrogen is going to be that carbonyl carbon, and then from the rest of that is going to be the rest of the chain. Now if the carbonyl carbon is not directly next to that hydrogen, say there's another carbon in between it, then it is something else. It is called a ketone. So the ketone is pretty similar to the last one that we just saw, except for instead of that H, it's going to have a different carbon chain on the other side. So for example, this one here, the full carbon chain is 1, 2, 3, 4, 5 carbons long. So if it were an alkane, we would call this pentane. However, it's a ketone. So this one is actually called 2-pentanone. Okay. Now, if we were to number these, let me go ahead and number these: 1, 2, 3, 4, and 5. Okay. The reason why it's called 2-pentanone is obviously the 2, the second carbon there, is the carbonyl carbon. So that's where that double bond O is going to be. Now, the reason we have to call this one 2-pentanone is because there's more than one pentanone. There can also be a 3-pentanone. So if I were to do a double bond O right there, that would now be 3-pentanone. Now there cannot be a 1-pentanone, because if it's a 1-pentanone, then it would simply not be a ketone anymore. It would go back to the aldehyde, because then the carbonyl carbon would be the one directly adjacent to the hydrogen. Okay. The next one is the carboxylic acid. Once again, taking a look at that carbonyl carbon right there in the middle. The difference with this one is instead of being the R on the left side and H on the left side of the aldehyde, or the R on the left side and another R of the ketone, This one is a R on one side and then an OH on the right side. Now, oftentimes a lot of people will get this confused with an alcohol, but since we have this carbonyl carbon, it is not an alcohol, it is a carboxylic acid. And these are quite easy to name as well. You just count the carbons, 1, 2, 3, 4, so this one has 4 carbons. So normally it would be butane if it were an alkane, but since it's a carboxylic acid, you remove the E and add an oic acid. So this one is butanoic acid. Okay, moving on. This is an ester. Esters are, once again, have that carbonyl carbon right there in the center. And then on the left side, we have an R and then OR on the other side. Okay. And to name this specific one here, you can kind of see that this one has that acetic acid almost, even though it doesn't have the H on the side, it has an R. So to name this one, it also has this ethyl on the side. So this would be ethyl acetate. Okay. All right, and the last functional group that we're going to take a look at, which is going to lead us into our next topic, is an arene. Now this arene is definitely probably one of the most common ones. It is benzene. So benzene is aromatic. Arene means aromatic compound. Now, the next topic I really want to kind of cover is aromaticity and the requirements for that. So there's 4 different aromatic requirements. The first would be it has to be conjugated, which basically means the pi bonds, it goes single bond, double bond, single bond, double bond, as you saw in the benzene. The next one has to be cyclic. Of course, it's always the rings. We've seen that plenty of times before, where we have the ring species. And the third has to be planar. The reason why it has to be planar is because of the p orbitals have to have good overlap with each other in order to form those pi bonds. And lastly, the Huckel's rule, there really should be a double dot over that U right there, but the Huckel's rule, which is 4n plus 2 pi electrons in a cyclic conjugated pi system. So the next slide I have is kind of showing 2 examples of an aromatic and not aromatic species. So this top one here, the reason why this one is not aromatic is it fails in the category of being planar. So this one cannot be aromatic because it is planar. However, the second one down here at the bottom, it is aromatic because it passes all those rules that we saw before. It's planar, passes Huckel's rule, it's a conjugated system. And so in order to confirm each one of these compounds as whether or not they are aromatic or not aromatic, it has to pass each one of those 4 rules in order to be aromatic. Okay. Now I kind of transition over into infrared. This is a good reference tool here in order to kind of identify what you have in terms of functional groups whenever you run it as a normal infrared spectrum. Now anything to the right of here, what I just drew there, is pretty much considered the fingerprint region. In the fingerprint region, we do not worry about that. But on the left-hand side of this, everything from 1500 up to the upper end there, 3600, we can take a look at those for sure. One big one that I want to take a look at is that OH, the alcohol functional group there. That's definitely a big one. So if we go to the next slide, I actually have an example where we can really see this big alcohol peak there. It's really broad, and that's characteristics of that alcohol peak, especially for this molecule. Okay. And so really what I wanted to get from this, even though we've kind of rushed through the infrared, is in order to identify each one of these, you really need to have that reference tool, which was on the slide before. Okay, moving forward to NMR. Once again, this is another reference tool. This is for the carbon-13 NMR. You can see plenty of different carbons attached to different functional groups, and carbons, double bonded carbons, halogens, etc., etc. And this is another one of those tools that you kind of need to take a look at in order to identify what you have in your C13 NMR. The next one, really, this is one of the most important ones in my opinion, in terms of the NMR series, is the PMR, the proton NMR. And once again, this is another reference tool to take a look at whenever you're identifying. Notice a lot of these overlap, so oftentimes it's difficult to pinpoint one specific hydrogen that you're dealing with. That's another point I wanted to take a look at, is each one of these, even though, let's take a look at this one, the aromatic alcohol. Even though that the aromatic ring and the oxygen are on the left there, the only thing this is taking a look at is the hydrogen attached to it. Just the hydrogen, just the hydrogen, just the hydrogen, just the hydrogen. So it's just taking a look at those hydrogens in the PMR, which makes sense, the proton NMR. So moving forward, since some of these overlap, we have to have some more rules, some more things we can take a look at in order to identify what hydrogens go with which carbons and which hydrogen goes with which molecule, in order to actually put this kind of puzzle together. So this is one of the ones I wanted to take a look at in terms of spin splitting. Now spin splitting is, let me go ahead and draw some hydrogens coming off these here, 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 and here. Okay, so we see we have two different kind of sets of peaks. There's an A and then there's a B. Of course, there's already labeled over here, but we'll just imagine we don't know what that is yet. So the difference between these two peaks looks like that we have 3 peaks here, and then over here we have 4. Okay, so what does that mean? Well, if we know that this is our compound, we can identify which is A and which is the B carbon in terms of this spin splitting here. So in terms of spin splitting, basically what you're going to want to take a look at is the hydrogens that are no less than 3 species away. So if I would say I was looking at this hydrogen right here, there is 1, 2, and then here is the 3rd. Now you're at another hydrogen. So what that means is, since it's connected within 3 different hydrogens here, this one doesn't count because this one is identical to the same hydrogen. What you're going to do is you can take those 3 hydrogens and you're going to add 1 number to it, so the 4. And so now we know that the one that splits to the 4th is going to be, this one right here. Okay, so you just add 1 number to that. Okay, all right, and so with the 3, you see the 3 peaks here, that one is going to be these hydrogens, because these are split by these hydrogens on the left side. You got that? You got that. Forward to really the last topic I want to take a look at in terms of NMR, and in terms of this presentation. You see there's some pretty advanced splitting in each one of these. The 2 on the right aren't as bad, but the one on the left is definitely really bad. So what we can do is we can integrate each one of these in order to see the relative abundance of hydrogen specific to that certain section of the PMR spectrum. Okay, so if we were to take a look at that previous, that previous chemical in the previous PMR spectra, we could integrate that, and if we were to integrate that, we would show that the ratio of the integration would be 2 to 3, because we had 2 hydrogens on that central carbon attached to the bromine, and then there was 3 hydrogens attached to the carbon on the right side. So whenever you integrate it, it becomes the relative abundance of each hydrogen. Okay, and I believe that is all I have for you today. So just in review, we talked about functional groups, aromaticity, IR, and NMR.